All right. Well, we're very happy to have Ennio Salvioni back after many years. Welcome back to Davis, and he was going to tell us about Gegenbauer Goldstones.
Okay. Yeah, thank you very much. I wish I could be there in a different way, but it's already great to see you all. I'll be talking about work that I've been doing recently with Gauthier Durier and Matthew McCullough. And it's still work in progress, so I'm especially interested in you stopping me at any time. So you should see this as very informal, as I guess you always do. So yeah, the topic is Gegenbauer Goldstones, and I'll tell you what I mean by that. I'll just start by a very basic introduction, which is this talk is about the Higgs, after all. So after 10 years that we know the Higgs boson exists, we still know not so much about what lies behind it, if you wish. This is the Higgs potential, as we know, and we really can see it as a very successful phenomenological model. We know these two numbers now, m squared and lambda, but we don't have a better understanding of what is underneath it. And an historical example could be superconductivity, where pretty much the same theory works effectively, but then we know that there is a deeper description that eventually was uncovered. And so the question is really if we can calculate this from a more fundamental theory. This is what ideally we would like to do. And another example of a scalar that is also a composite, if you wish, but that is more close to the problem is the case of the pion QCD. Sorry, let me change this. So we know that the pions are QQ bar quark-antiquark bound states, and that they are Goldstone bosons in first approximation. So the old question that I'll be asking again in this talk is whether the Higgs field could be something similar. It could also be a pseudo-numb Goldstone boson, PHGB particle. Of course, this has a very strong history that I will not recap completely, but I just want to point out to one aspect of it, which I'll be discussing today, which is that there is an important difference between the pion potential and the Higgs potential. And the difference is really sketched in this slide. So for the pion potential, here I just took the contribution from the quark masses. We know that the minimum sits at 0. This is the neutral pion. Okay, so the potential takes a form of this type, a cosine of pi over f. While for the Higgs, there is spontaneous symmetry breaking, so we need to get a non-zero VEV. Okay, so here the pi h is non-zero at the minimum. And we also know by now that this minimum has to be, this value has to be much smaller than the overall scale of the nu that the Higgs as a Goldstone originates from, which I'll call f. And this is because we have measured the couplings of the Higgs to a level of 20% or so by now, and the couplings of the Higgs are corrected in a form that is like this. So we need V over F to be much smaller than 1 in order to comply with this constraint. Okay, so the question that I'll be asking is how to get this. Okay, how to obtain V much smaller than F. Naturally, this is a question that has been addressed several times and is a big issue in the framework where the Higgs boson could be a PNGB. Okay, so that's the motivation. Now, to do this, I'll start with a very basic 2 slides on this. So the abelian case, which is not relevant for the Higgs, but is relevant for the story. I think it's the best way to get there. And then I'll discuss the non-abelian case, so what these Gegenbauer Goldstones are, and then I'll discuss 2 applications to the physical case, so the Higgs boson and also the twin case. But I'll come to that. Okay, but the first 2 are general. I will not really rely on composite Higgs or similar ideas for the first part of the talk, which is supposed to be a bit more general. If you have any questions so far, please stop me. Otherwise, I'll continue. And yeah, for a single Goldstone, all I want to say is, let's say that there is a complex field, a scalar field phi with a spontaneously broken U1, okay, which arises from such a potential. Okay, then at this level, the Goldstone is massless, and I can make it a pseudo Goldstone boson by some explicit breaking. And I'll assume here that the explicit breaking is from an operator of charge n. Okay, so I get something like this as an explicit breaking term. And we know that if we do this, then the resulting potential is nothing but the cosine of n pi over f, where pi is the Goldstone boson. okay, which we see by parameterizing the angular mode in this way of the field. So this is a periodic potential, and we know where it comes from. Okay, we know that there is a discrete symmetry that underneath it, which shifts the pion in this way. Okay, and so this is a very simple way to get, for an abelian Goldstone, the web to be very small. The pi over f at the first minimum here is parametrically pi over n, and if n is largish, then this is much smaller than n. Okay, this we know. Okay, and the question that I'll be asking is how to translate this to a non-abelian case, which is far less trivial, because in that case we will essentially lose the periodicity of this, and then this is where what we try to do. But before moving on, I want to also say that there is related work by Anson Hook of a few years ago. Now, he did something quite different from what we did, but I think this work was influential, at least for me, in thinking about these things. So I think it's fair to acknowledge that. I can tell you about the difference if you're interested, but it's really not the same logic in many ways. The parallel sort of stops here. Okay, so this is what I said. This is a standard class of radiatively stable potentials for the abelian case. Right? This we knew. Now, what I want to do next is the case where instead we try to do the same for the non-abelian structure. Okay, hopefully this gets a bit less trivial. So in this case, let's say that I'll take the simplest case, or at least the case that I'm interested in for in a Higgs perspective, which is SON plus 1 spontaneously broken to SON. This gives us n Goldstone bosons, and now, of course, this is a non-abelian symmetry. The potential will formally look very similar to before, okay? And the question that I'll be asking is how to get the VEV of this multiplet to be much smaller than f, the overall scale. Yes. So the parallel goes in the following way. So if I want to achieve something like that, I'll assume that there is not only a spontaneous breaking, this potential breaks spontaneously, SON plus 1 to SON. I'll also assume an explicit breaking to SON, okay? And I'll do this by taking a spurion, which is in an n-index representation of SON plus 1, okay? So this is an index, a tensor with an indices, which is symmetric. And I write it as this kappa element here, which multiplies n instances of the phi field, which is a fundamental of SON plus 1, okay? This is really analogous in a sense to what we were doing before, just that it's important to notice that because this is an near rep, the tensor has to be traceless, okay? So I'll also have that as a condition. And at order epsilon, where epsilon is the small parameter, that is in front of this breaking, this is all that I can write essentially, okay? If I have only one multiplet of fields, then this is the only structural tensor that I can, invariant that I can build. Okay, and so any correction would have to at least come at order, for example, epsilon squared or higher. So if I do this, which is my non-abelian analogy of the previous case, then what I will show you now, but I'm anticipating the result, is that this potential really is a Gegenbauer polynomial. Okay, and the way to see this here is I'm doing the same as I was doing before. I write the phi field, the linear field, as an exponential. Now I have, of course, a non-abelian set of generators, but the logic is similar. I get this form, which is the form of the nonlinear field for a nonlinear sigma model. And if I do a little bit of math, which I'll do in the next slide, I arrive to this form. Okay, so the point is that the equivalent, in a sense, of the phi to the n explicit breaking for the abelian Goldstone is a Gegenbauer polynomial. Okay, that's my claim. Yeah, and I should say, a lot of what I'm going to say now was already found, of course, 50 years ago by Zinshan and collaborators. Just that they applied this in the case of two-dimensional nonlinear sigma models. That's what they were interested in at the time. So I think some of it is we are rehearsing this story in the case of 4 dimensions and the Higgs. So this is how you really get the Gegenbauers, and it's actually not difficult. So what the starting point is this scalar function here, okay, where n is the SON in the problem. Okay, and I can do two things to it. On one side, I can do a Taylor expansion, which is written here. Okay, I'll take this as a function of phi and I'll Taylor expand it, where my coefficients of the Taylor expansion now are tensors, kappa n, which are the tensor I told you before. Okay, and on the other hand, I can remember what phi is. Phi is my nonlinear field of a nonlinear sigma model, so it has a form. Let me go back a second. It has this form here, which is sines and cosines, as usual. And I can write this as basically as the generating function of Gegenbauer polynomials. Okay, the generating function of Gegenbauer polynomials is this one in general. This is just a mathematical definition. And I can recognize it in this form and notice that I can also expand it as a series, okay? So the bottom line is that identifying the two ends of this equality here, the tensor multiplied by n instances of the nonlinear field is equal to a Gegenbauer polynomial. Okay, that's the logic. And one thing that I didn't say is that these tensors are also traceless, and they are traceless because if you have an object like this and you take traced any two indices, you get the Laplacian evaluated away from the origin, okay, evaluated in this vector phi tilde, which is my explicit breaking direction, and this is also vanishing. Sorry, I'm having some trouble with the cameras. Okay, very good. Yeah, so let me stop before I continue. Any questions, any complaints? Okay. So this is the bottom line. From an explicit breaking of SON plus 1 to SON, we get Gegenbauer polynomials. And I'll stop for 1 minute to just say a few words about this. So what are Gegenbauer polynomials? Some of you will be very familiar with them, perhaps not everyone. So then they carry the name of Leopold Gegenbauer. And they really can be seen as the generalization of Legendre polynomials to dimensions different, space dimension different from 3. Okay, so for example, here I put the case of d equal 3, which is the one that gives Legendre, and we know it's if I have a certain function that is axisymmetric as an SO2 remnant symmetry, then I can expand it as a series of Legendre. And the same I can do in the dimension different from 3, spatial dimension different from 3. They appear in many places, and one example here, but I just put one, and there are many, is the expansion of conformal blocks. In conformal field theory, they appear naturally there. And here, the only difference with this case is that here they really arise from explicit breaking of an internal symmetry. And so the variables are not really space-time coordinates, but they are PNGB fields. This is the only difference with that setup, really, but the math is of course the same. Okay, so there is so far what we discussed is that these Gegenbauers are sort of the non-abelian analog of a charge n operator in the abelian case, if you wish. There is, however, another way to find them, find the same answer, which I think is interesting to do, and I'll do it in 1 minute here, which is that without knowing anything of what I said before, you could also find them directly by looking at the condition of radiative stability. So if you take a generic potential written in this form, okay, which is SON invariant, pi is just my vector, the modulus of the vector of Goldstones here. And I look at the quadratic piece of the one loop Coleman-Weinberg, then I get this expression. This is the original potential, okay? And this is what the leading correction looks like. And this you can calculate in the standard way using, for example, methods in these papers by Manohar and collaborators. And what you find is a correction of this type. And so this tells us that if this term here were to be proportional to G, to the function itself, then we would have a multiplicative renormalization at this level. Okay? It would not be a different function, it would just renormalize the coefficient of the whole G. And in fact, what turns out to be is that the Gegenbauers do satisfy precisely this equation. So this is another way to define a Gegenbauer polynomial, which is through this differential equation. So you see that the first two terms are appearing really here. And this tells us that this alpha parameter, which is a general index of these polynomials, has to be identified with n-1/2. I mean, if this is... Yes, please.
I want to ask probably, what property do you want Gegenbauer polynomial? I mean, why you choose this particular polynomial other than other polynomial?
Yes.
What
So
property do you want from it?
yes, very good. So the motivation is to get a minimum that is parametrically close to the origin. So say it again.
Without fine tuning, that's your motivation.
Yes, exactly. And I'll come back to this basically in the next slide, because that will be the end of this part. But yeah, absolutely. So the motivation is I would like to see if I have a parametric way to get V over F much smaller than 1, or a minimum as close as possible to the origin. Yeah. So I'll show you in a second that this is what I use. So, sorry for the detour.
Sorry, can I just ask before you leave this?
Yeah.
I mean, this raises the question, the Gegenbauers would solve that differential equation with some specific boundary condition, right? But you could now imagine trying to find, using other boundary conditions to find different multiplicatively renormalized potentials. Is there some reason why, from this point of view, you're picking out the Gegenbauer polynomials?
Yeah, I think that's a good question. So,
Right, I mean, wouldn't you think, just like Legendre polynomials, there are like, aren't they like I forget, the associated Legendre functions? Maybe they're singular. Is the other solution singular or something?
yeah. So the partial answer to, I don't think I have a complete answer. The partial answer is that whatever we looked at so far, we thought about this a bit, was singular. So it had some point where it looked like it was coming from something that was was non-analytic, if you wish. So there was something light that we had secretly integrated out, if you wish. But
the polynomial, then I'm sure it's unique, right? If G is literally, if you really require that G is a polynomial, but it's not obvious why you should want a polynomial in cosine pi over F.
Okay, the polynomial of cosine pi over F is coming really from the requirement that I have an SON invariant.
Yeah. But I mean, you started this conversation, right? You said you can understand it the other way around. So I'm saying you can also just say, I don't care about that now. All I care about is multiplicative renormalization.
Absolutely. Then if I drop that condition, yeah, that's fair. If I drop that condition, then I have certainly, I should have more options, at least in principle. Yes.
Okay, that's fine.
Yeah. No, that's good. So yeah, so this is at least one possible solution. And yeah, okay, and n equals 1 recovers the abelian case, in the sense that here the condition will simply be that g double prime is proportional to g, which is solved by the cosine of n pi over f. Okay, now let me answer the previous question, which is important, and of course I have been delaying it. So why do we are we interested in this? So this is how a Gegenbauer polynomial looks like for a certain choice of indices, which is not so important because this is really just illustrative. Okay, this is n equals 4, capital N, which is basically SO5 to SO4. And the choice of n is equal to 20, and it's large to emphasize this, but it will not need to be this large eventually. So the point is that this first minimum, okay, is at pi over f, which is approximately 5 over n. Numerically, this is some 0 of a Bessel function. And for large n, you get 5 over n. So there is a parametric sense in which for large n, this becomes close to the origin. Okay, so this is why I would say it's a parallel to the case of abelian Goldstones. And so this is, yep.
Is it blowing up at 0? Potential?
I don't think it is blowing up. I think it is going to a finite value that is not in the plot. Yeah. Yeah. So yeah.
There's a chat from Manya. Did you see that?
Oh no, sorry. Chat is. So I'll read that. Did you see it? Well, I'll read it.
Yeah.
So associated Legendre require extra integration constants. The second solution to the ordinary Legendre equation is singular at both ends of the interval and not normalizable. The same is true for Gegenbauer. Okay. Yeah, yeah, that's referred to the conversation that we were having with Marcus. We can come back to it later in case. Let me. continue. So yeah, so the other thing I wanted to say is that differently from the billion case, this is not periodic, of course, although there is a sense in which it's approximately periodic in this region, okay, in the middle region. So for a little far from the first minimum, then you can expand it and find that it approximately does behave like cosine of n, as shown here, okay? So let me summarize this first part, which is more general. So what I think this says is that the Gegenbauer polynomials are the building blocks of potentials, which in this case I chose to be SON invariant, okay? And so this means that the generic potential can be expanded in this basis. This is just a complete basis. And if we just have one, we happen to have one of these polynomials dominating the potential, then this is going to be relatively stable in the sense that the coefficient will be renormalized at order epsilon, but the functional form will remain the same. And so the bottom line is that this is at least a technically natural way to obtain a small VEV parametrically in the non-abelian case. Okay, so this is the formula that I was recalling. Now let me stop again. If there are comments, then the next step will be to apply this to the Higgs story. That's what I want to do as in the second part.
So you want the very large little n, right?
Yes. So at this stage, looking at this, you would want indeed n to be very large. What I'm going to show is that once, so the potential for the Higgs will not be just a Gegenbauer, because we know that there are some irreducible explicit breaking effects that we need to include, the top quark mass, the gauge interactions, and so on. And once we include those, actually this tends to decrease n. So at the very end, I'll show you that n will not be larger than say 10 or so in practice. But yeah, parametrically, this works for large n, absolutely. So so the detailed answer requires to look at it more carefully. Okay. Oh yeah, sorry, I forgot this. Of course, this is not the only way to try and take seriously this V over F tuning, so getting a separation here. And I think the other way that is very interesting is to use tadpole-induced electrosymmetry breaking. So this is, of course, something that Marcus has pioneered in the past. And there is also this nice paper by Ronnie Arnick and collaborators that looked at this in the context of PNGB models. And I don't have more to say in the sense that I think that there is an updated analysis which, with the latest bounds from the LHC, is sort of missing on this. So it's not completely clear to me, at least, where do we stand here. But I think it's worth mentioning. It's a possibility that does work in that sense. Okay, so now Gegenbauer Higgs, and here I have just one slide of introduction to the framework, which most of you absolutely don't need. But the idea is composite Higgs models with partial compositeness. That's what I have in mind as a framework. So I have this strongly interacting sector where there is some spontaneous symmetry breaking, which I'll take to be SO5 to SO4. So the minimal version that gives us a custodially preserving Higgs. And F will be interpreted as some M star over G star, where M star is the overall scale of the new sector and G star is the typical coupling, which we will want to be somewhat large. And these couplings here of the fermions of the standard model of the gauge bosons break explicitly the global symmetry and generate some irreducible potential, if you wish. Because of the idea of partial compositeness, which is that the mixing is of fermions in particular is proportional to their masses, the largest contribution to this potential comes from the top quark. And this is also a well-known story where the top quark is really the reason why there is electroweak symmetry breaking. Okay, so in a sense, the top loop and top partner loops tend to have a negative sign and get us a negative mass term which realizes electroweak symmetry breaking. So that's sort of the basic picture, old and well established. Okay. And so this is how it sort of works very roughly at the level of the potential. So here I just write a typical contribution from the top sector with a negative sine square term and a positive sine to the fourth, so a negative mass and a positive quartic, first approximation. And what is important to notice is that there is a certain minimum size to this, which is given by the mass of the top partners. Okay, so the top partners in this picture have color. Okay, they are QCD charged, and searches at the LHC tell us that these particles cannot be lighter than, say, 1.3 TeV by now or so. So this sets a lower bound on the size of the potential that we have to keep in mind. It is there. And a potential like this also requires generically some tuning in order to achieve V much smaller than F. There is no principle why this would be the case. And so there is this tuning, which is what I mentioned. V over F squared is the size of the tuning. This is all very, very standard. But it's important to introduce it this way because then we can understand what we will change in trying to address this problem. And what we will try to do is the following. So we will take, instead of an electroweak breaking top contribution, we will take an electroweak preserving top contribution. Okay, which means this sign will be positive here. And this may not be very familiar, but it's actually a reasonable possibility. So there is no theorem saying that the sign of the top potential has to be negative. We typically want it to be so because we want electroweak breaking to come from there. But if you look at a model, and I can show you if you're interested, typically this is a split situation. So that there is a parameter space where it's positive, there is parameter space where it's negative. There is no a priori preference. So this is what we'll do. We'll take a positive contribution from the top, and then we'll add on top of that the Gegenbauer contribution. Okay, so this is here a Gegenbauer polynomial. And what I have in mind is that the Gegenbauer contribution is sort of internal to the strong sector. Okay, so in an equivalence, sort of in a parallel to QCD, this would be coming from really something like the quark masses in QCD. So an operator that is really not depending on IR physics necessarily, not the gauge interactions, for example, at the electromagnetic loops in QCD, but is coming really from the UV theory. So this is the potential we look at, and this potential, once we combine the two, looks like this. Okay, depending on this gamma C over gamma, which is a parameter. Gamma C is a certain value, which is a critical value below which the minimum is simply at the origin. Okay, if gamma is too small, then the minimum is simply just here, and as soon as we cross this gamma C, then there is a range of possibilities. So let me show you what can happen. So there are two limits which are easy to understand. On the right here is the limit where the Gegenbauer contribution here is dominating. This is the large gamma limit. Okay. Then what happens is easy to understand. There is no tuning to get V much smaller than F, because that's the whole point of where I started from. However, we need to tune to get the Higgs mass right. Okay. This kappa parameter in front of the overall potential needs to be small. Okay. And that's a quantification of tuning. I just need to pull down the whole thing.
Well, what's the definition of gamma C? Did I miss it?
No, sorry. So gamma C is a certain numerical value, which is the critical value separating. So below gamma C, okay, the minimum is just at the origin.
Okay.
And as long as gamma is larger than this, the minimum is always displaced. It's a sort of a minimum value size of the Gegenbauer. Yeah, sorry, I didn't explain it carefully.
Right.
Okay, so this is the regime where the Gegenbauer is winning. And the other possibility is instead the other end of the plot. Here, the Gegenbauer is just a perturbation. And you see it's clear, right? It's just giving a little tipping of the potential here. So here, there is no mechanism that would get a small VEV. There is tuning. So we need to tune to get the VEV. However, the mass of the Higgs comes out about right. Okay, this helps a bit with the mass, and so there is some help from this size. Okay, so nothing works at either end. There is a problem. That's the conclusion. Here we need to. Yep.
What's kappa? What's your definition of kappa?
Kappa is here in front of the all potential.
Oh, I'm sorry. Okay, thanks.
No, and thanks for the question. Let me also say this parameterization is partly unfortunate for the following sense. Kappa is multiplying everything. Okay, so it's also multiplying gamma. However, this is not important. So it's just a convenience choice. The point is that when I make kappa small, I am suppressing the contribution from the top sector. I need to tune to do that. There is no reason that allows me to do that, but this is sort of parameterizing that tuning. Okay, imagine that kappa is the difference of two masses, for example, and I need to get those two masses pretty close in order to suppress the contribution. That's what happens in practice.
For this example, what's your value of gamma C?
Oh, the numerical value of gamma C is very small. It's of the order of 10 to the minus 4. I think in this example, I can look it up though. I don't remember the precise number, but it's what was the concern there?
No, I just want to see the relative size of the two terms.
Okay, yes, it's a small effect. I think it's of the order of a few 10 to the minus 4 here. Okay, so bottom line is that there is an issue on either side of this plot, and the best compromise one can get is really to sit somewhere in between. Okay, so let me show you the.
All right, I'm just puzzled by your saying that. Are you really saying that the ratio? Sorry, gamma is really the ratio of the Gegenbauer term with the sine squared term, right? So just the numerical value of gamma, you're saying, is of order 10 to the minus 4?
Yes, let me, since I have it here, let me look it up. But yeah, I'm pretty.
That sounds a little, it just sounds a little weird, right? Because you don't want huge numbers in, where is that so, that number just sounds really small. Can you explain why that is so, why the gamma is so small? Can you say something about that? It doesn't seem like there are other numbers that are that small here. So I'm just wondering where that number is coming from.
No, I understand the question. At this level,
bigger gamma is okay, right? As you show in your figure. The problem is just the Higgs mass would be too heavy, something like that.
So that is true. So the value that is 10 to the minus 4 is gamma C, which is when I'm sitting here. Okay. So
yeah.
in some sense, in that case, I'm definitely tuning. Okay. So maybe that's a partial. I don't know if that answers your question, but I don't have a reason for it being small, except that it's an explicit break-in that I'm sort of assuming that it's a small effect.
I mean, yeah, you can assume that it's small. There's no problem with that because it breaks symmetries, and so it's multiplicatively renormalized. I'm just wondering why it came out to be 10 to the minus 4 to be at that critical point, because somehow at the critical point, the Gegenbauer is competing with the sine squared term, but there's no, why would that happen at 10 to the minus 4 rather than something like a third or something?
I think it may just have to do with the normalization of Gn.
Oh, and maybe n is 20, so somehow there's secretly a.
Yeah, so I don't remember the prefactor.
It's okay.
But I suspect, I understand your question now. I suspect that the Gn comes with the n to some, but let me, since we are here, let me actually tell you the precise number. Yeah, okay. It's a few 10 to minus 4 gamma C. No, I was just making sure that I didn't misremember, but it is.
Okay.
In this case, no thanks. Yeah, that's great. Okay, yeah. So the compromise will be in the intermediate region. Okay, and this is not completely satisfactory, of course. This is the plot that I want to show for the tuning. So let me be slow here. So this plot is showing two things. depending on whether the contours are solid or dashed. So this is on the left, and solid are the lines of the VEV tuning, okay, which are, for example, this n equals 4 and n equals 10. And here they just decrease, so the tuning gets worse as we increase f. This we expect. Okay, and on the right in dashed lines is the tuning due to the mass, mass of the Higgs, and this has the opposite behavior. Okay, and in this plot I'm fixing the lightest top partner to be 2 TeV. So the idea is that this model won't be seen at the LHC in a certain sense. I want to see how bad the tuning needs to be for that to be true. Okay, and the bottom line is that this compromise that I was talking about, for example, is realized somewhere like here. Okay, in this case, which is f equal to 2 TeV, both tunings are at the level of 30% in this definition. Okay, and so what we have here is the following. We have, sorry, let me move this. What we have is f equals to 2 TeV, which means that the corrections to the Higgs couplings are very small, below 1%, which we will not see even at high Lumi LHC, or probably not. And the total tuning, if I multiply the two very naively and roughly, is of the order of 10%. Okay, so that's a sort of semi-quantitative conclusion. There is an improvement of a factor of a few with respect to the standard story, where the tuning would be 2v squared over f squared, which is 3%. Okay, so, and the other thing is that you see this is achieved for n equals 10 in this example. So this is going back to what Sincha was asking before. And the reason for this is that if I were to increase n too much, then, for example, I would be getting significant tuning from the Higgs mass. Okay, so in practice, I don't want to go to n too large. This is sort of my optimal point here.
Well, do you have to tune how many parameters are you tuning? Kappa and anything else?
Let's say I'm tuning Kappa, and if needed, I'm tuning Gamma. The one, yeah, let me go back.
And you just
yeah, here.
Okay.
Yes, so it's Kappa, the overall size, plus Gamma, which is the VEV tuning, is deciding where the minimum is.
Multiplying them together to get your 10%.
That's right. And yeah, so this is, I think, the partial conclusion. Let me see if yes, this is the partial conclusion. And one last word about this is what happens to the corrections that I talked about here are single Higgs couplings. For example, Higgs coupling to the Z boson or to fermions will be corrected in general at this order. However, the trilinear Higgs coupling could be different because we are looking at the potential that is very different from the standard model in a sense. And in fact, the pure Gegenbauer potential has a completely different shape there, in the sense that the trilinear is about -1 in this model, in standard model units.
Wow.
This is purely academical, though, because in practice, that's overridden by the top contribution. So if you really look at the plot that corresponds to what I showed you so far, here, where now the top loops are included, you see that the point I was referring to is sitting here. Okay, so the correction to the trilinear is about 10%, slightly smaller actually. Okay, so in principle, there could be a sort of a dramatic difference, but in practice, the effect is actually very suppressed. And so 10% correction is something we will not, unfortunately, see at the LHC, for example. We need to wait, perhaps, for FCC. Okay, but still, this is interesting a priori, and so I'll come back to this in the last part of the talk, which will be applying this story in the twin case.
Sorry.
Yeah, please.
It looks like from this plot that it wants to asymptote to the standard model when f is large, and I would have, you might think, oh, well, of course, because when f is large, you're just tuning towards the standard model. But this is coming from a loop correction, so somehow getting the standard model requires the loop. I mean, do you understand that why these are asymptoting to the standard model for large F when it's a loop correction? You understand what I'm saying?
You mean loop correction from the top sector?
Yeah, because I would have thought that if you just had some model that you could tune to the standard model, then at tree level, when you make F large, at tree level, you should asymptote to the standard model, right? All predictions should asymptote to the standard model. But you're telling me that it's loop corrections that are doing this, and I'm thinking, why should loop corrections get you within 10% of the standard model? That seems weird.
When I say loop,
Loop
you mean the top loop?
Standard model, the same way.
Oh, I see. That's the point. The point is that when you say standard model, you're saying, yeah, the top loop is also becoming the extended.
That's right.
Top loop. I see. Okay. So that's what it is.
Yeah, exactly. That's the.
So it is just the decoupling. Everything is decoupling as F gets large.
Yeah, indeed.
Okay. Okay.
Sorry.
So yeah, so in some sense, it's not a huge surprise because everything here is decoupling as it's different from the tadpole case, right? The tadpole case, it's a truly non-decoupling contribution, and so you do get a large contribution to the cubic. I was just trying to understand that.
Absolutely,
Okay.
absolutely. No, and this is important because it will, at the very end, in a few minutes, we will come back to this in the twin case, and then it will be sort of neater in the sense that then the top loops are smaller, and so the Gegenbauer will win in a sense.
Okay. Thanks.
Okay. Oh, sorry. Yeah. So summary for this before coming to the last part is this. So in principle, this could work. I think for standard composite X models, but the main issue is that what we know by now from the LHC is that the top atoms have to be heavy, not a surprise. And so the contribution from those loops is just too large for a Gegenbauer contribution to be dominating, if you wish. And so there is some tuning that remains, which is a fact. And even though the Higgs cubic coupling could be also very different from the standard model, in practice, it turns out to be already close to this decoupling limit in a sense, as we were saying. Right, so this is a partial conclusion. Now, let me stop if there are more questions, and then if not, I have a few minutes of the last part.
Okay, I want to ask maybe very naive question for the gamma, the sign of the gamma maybe matter, right? Does the sign of gamma matter? That's my question first.
The sign of gamma. Yes, it does.
Okay, so my last question is, I remember in QCD, at least in vector like gauge theory, there are some signs to be positive, some potential to be positive. Like I think it's some kind of weighting theorem or Weinberg theorem. I forgot. So is there any constraint on gamma from your symmetric weighting pattern? There's on the sign of gamma. That's curious. Or there's no constraint at all on the sign of gamma.
Not that I know of. I understand the question. Not that I know of. But yeah. So at this stage, I think that's partly related to the question, if you wish, where is gamma coming from? Yeah. Of course, which is a question that I'll come back to at the very end, but I don't have an answer. I can anticipate that.
This is breaking, right? It's not a spontaneous breaking.
Yeah, I mean, maybe this. So you have a dimension 10. If you have n equals 10, you have this is a dimension 10 operator, right? If n is 10, right? Here you show n equals 20, but I'm saying for your best point, you had little n equals 10. That's
yes.
The number of powers of fields, so that at least at low energies, that's a dimension 10 operator, right? So from the bottom up point of view, that operator is going to get strong very fast, right?
Yes.
Very operator. So, where does this, from the bottom up point of view, do you know when this theory breaks down? For your favorite choice of parameters, have you checked where it gets strong?
No, we have not. But also, let me say, So I don't know how to best phrase this, but I think it's not, to me, it's not completely. So you say correctly that you know, there are this Gegenbauer with the n index equal 10 has a 10th power of a sign, say, okay, sign to the 10th,
Right.
and is a series up to that, and that's correct. But in a sense, yeah, I think there are very strong cancellations among the different contributions to this series. Okay,
Yeah.
so the overall size of a Gegenbauer is way smaller than individual terms, if you wish. So you say you're interpreting that as the theory becoming strong at low scale.
Yeah, I think it, I mean, let's talk about this afterwards. Why don't you finish your talk? Because this is, you know, actually Ricardo Rattazzi and I have been talking with Anson Hook about these things, these kinds of issues. So
Okay, I'd be very interested in
tell you what I know or I remember.
okay. So let me I have a few minutes on the last version, which is the, so sorry, let's go back to the, yeah, so we were here. Okay, so what I'll do in the last few minutes is sort of the obvious thing. So in the previous case that we discussed, the problem that sort of was forbidding the story to develop as one would hope is that the top loops were too large. Okay, and then there is a natural way to solve this, at least in principle, which is to make the top partners colorless. Okay, if the partners don't have color, then it can be much lighter than what I told you before, and so the overall size of the top potential can be naturally much smaller. This is what one gets, and so this is why we sort of rehearse the story in the twinings context. So yeah, this is already what I said. The Gegenbauer story can do V much smaller than F naturally in principle. And twinings models can reduce the size of the top contribution because they have, by construction, QCD neutral top partners. So the idea was perhaps we can marry the two and get a theory that is fully natural for electric braking. That was the point. So very briefly on the ingredients for this. So the twinings is a theory where there is a mirror copy of the standard model, and what is important for what I will say, I will take the simplest version where everything is twinned. Okay, so there is a full mirror sector, the whole standard model as a second copy, and the structure of the potential, which is what I'll care about here, is SO8 invariant. So we have a standard model Higgs, HA, and a twin Higgs doublet, HB, and their potential as this SO8 invariant form. This breaks spontaneously SO8 to SO7, which is again in the same class that of breaking of symmetries that I was mentioning. And of the 7 Goldstones that come out of this, 3 are eaten by the electroweak gauge bosons in the twin sector, and 4 make up the Higgs doublet. Yeah, this is how the cancellation actually works, or sort of why twinings helps protecting the Higgs mass. This is because at the level of quadratic corrections, the potential has an enhanced symmetry. Basically, when we have this exchange symmetry to be exact, then the quadratic corrections are accidentally SO8 invariant, and so there is no contribution to the mass of the PNGBs. Okay, so to make the long story short, this is a solution of the hierarchy problem up to a scale at most 4 pi f. Okay, so about say 10 TeV or so. This can work.
Sorry, maybe when you question, I did not remember correctly. You say two symmetry are element of SO8, or your actual assumption? Is the two symmetry is element of SO8? Or the impose additional two symmetry?
It's an additional condition. It's an additional condition. So I'm just assuming that there is an exchange symmetry. And
SO8 cross Z2. That's your starting point.
It's an SO8 cross Z2, and the Z2 exchanges the two SO4s inside the SO8, if you wish. Yes.
You like 08, right? If you want to really.
I think SOA is extent of Z2 is exact.
Z2 is element of SO8.
Yeah. So
It's not.
it's
So I didn't.
enhance the symmetry, right? Once you have this Z2 on the quadratic term.
Well, what I mean by Z2 is that I needed the two Yokavas to be the same here, right? So
I mean that's late, but you assume Z2 from the core interaction. You assume the explicit breaking of SO8 respect Z2. That's
yeah. Yes, in the sense that each of these two Yokavas does break explicitly SO8, as you point out, and the exact protection will work if the two are equal at a high scale. At a high scale. Yeah, no, thanks. It's good. I mean, this is the point. Okay, so when I write a Yokava like this, the top partners can be charged under a different gauge group, which is twin QCD, and in particular, they have no standard model charge. Okay, so the twin sector has its own gauge symmetries, but they are not the same as the standard model, and this means that the top partners can be very light in principle, compatibly with what the LHC has told us. Okay, so that's the summary. Now, the more interesting part is how the potential looks like. So at the quadratic level, there is this protection I mentioned. At the quartic level, there is no such protection. There are contributions to the potential, which take the form written here, sine to the fourth of x over f plus cosine to the fourth of x over f. This is still Z2 symmetric, this potential that I'm writing, but it now breaks explicitly. There is an explicit breaking of SO8, and so there is indeed a contribution to the PNGB potential. However, this by itself is not enough, in the sense that such a potential gives either V equals 0, no electroweak breaking, or V equals F, which is ruled out because of Higgs coupling measurements. Okay, so the zero order twin Higgs model doesn't work as an electroweak breaking theory, and one needs to do something else, some other Z2 breaking, which leads to the tuning that I started with. So there is always a V squared over F squared tuning in these models. Okay, and that's the status. And so what we did was simply to say, okay, let's take this potential, and instead of adding a Z2 breaking, let's add a Gegenbauer contribution. Okay, and it's very similar to what I said before. The only technical difference is that now the explicit breaking is of SO8 down to SO4 squared. Okay, and in particular, this potential that I'll be using actually preserves the Z2. Okay, for even n, the potential is also respecting the exchange symmetry. So the total potential is the sum of these two pieces, and now we can repeat the analysis that I did before. Okay, but with the smaller potential. So these are the two parameters: this A that enters in this log, and this epsilon, which is the overall size of the potential. This was gamma before. Now we'll call it epsilon. So this plot is basically the bottom line. So this is showing the tuning delta divided by the standard tuning that you get, which is 2V squared over F squared. Okay. So for reference, this black line is the sort of a typical twin Higgs model. Okay, where actually the reason for electroweak breaking is that the twin hypercharge is not gauged. Okay, so there is a small effect from G prime in the standard model being not compensated by G prime in the twin sector. And this ratio you see is for optimal values, a Gegenbauer with n equals 6 or 8, for example, it is about a factor of 4. Okay, so we gain by this factor, which is numerically roughly 4. So this sort of is showing already that this can go in the right direction. And now the same plot, but showing the absolute tuning. Okay, so trying to really quantify how much there is this. So this is tuning delta versus F. And you see that if I take n equals 6, for example, the orange line, okay, and I sit at the best value or around F equal to 1 TV, the tuning is something like 0.5 or 0.6, okay, which at this point is sort of a natural breaking, I would say, within the limits of the fuzzy definition of tuning. Okay, and so yeah, so this is the bottom line. In this case, it can work. because of course already the tuning of the standard twinings is pretty good. We have about 10% for one TV. Here, this factor of 4 or 5 that we gain brings it to be sort of fully natural. That's the summary. So before concluding, let me just show you the trilinear coupling, which is, I think, the last bit. So now what we were discussing before really happens. So the potential is dominated by a Gegenbauer, and so the trilinear is very different from the standard model. So for example, if you look at f equal 1 TV, which is my imaginary benchmark here, then for n equals 6, I'm sitting at 0.3 or so in units of standard model. And if I have n equals 8, I am sitting at minus 0.5 or so, or 0.3, 0.4. Okay? So these are very far away from the standard model. And in fact, in principle, they can even be tested at some level at the LHC because the sensitivity is roughly to half of the standard model value by high Lumi. So yeah, I think in principle, it is possible even that this could be a first hint to a deviation in X couplings at the LHC.
Have you have a look at the quartic Higgs coupling?
The quartic, yeah, we looked at it indeed, and it is a factor of a few even different. So for these values, these benchmarks I was telling you about, it would be a factor of a few away from the standard model. The problem is that experimentally, it's a very difficult problem. So the sensitivity at the LHC is almost non-existent. So even at the FCC or future colliders is relatively limited what one can do for the quartic. So we found in practice, I mean, in principle, yes, I agree with you, but based on what people think right now, it would be a bit difficult to learn something from there. But it's a good point. It's different. And okay, so that's the end of it. So this version of it, Gegenbauer's twin, shows that at least in principle we can still get natural electroweak braking. But one thing that one has to do throughout is to drop some assumptions, and in particular the assumption that explicit braking should come in sort of minimal or small representations is one of them, which is important. Okay, so this is clear. And a general question, which I don't have an answer yet, but it's an interesting one, is whether one can get something like this accidentally. So of course, we would want a theory where the lower dimensional operators, smaller n, cannot arise because they're forbidden. For example, they're forbidden by gauge symmetries for the underlying constituents and so on. And so this is something that we are thinking about. Other things that I think are one can explore are first the idea to construct a Gegenbauer top sector, meaning that instead of introducing this additional braking as some UV spurion, we could get it already from what we do need, which is top loops. And this is in a sense more similar to what Anson was trying to do in the abelian case. This is what he really achieved in there. And also the question in general is what happens if I have another coset, because for example, I'm not sure what are the special functions that one gets there and so on. So this is something that we should look at also, but I don't have at the moment something to say. Okay, I think that's it. So thank you very much, and I'm happy to take more questions.
I can tell you that you may have. Let me tell you something about the strong coupling issues. Okay, so
yes,
so, you know, back when Anson put out this paper, Ricardo Rotazzi and I were with him in Santa Barbara, and we sort of quickly realized there was something fishy in his paper. Okay, and there is. So it has to do with the strong coupling. So,
okay.
So you might think, oh, is it really clear that the, you know, if you have large n, does that somehow correspond to stronger coupling? And the answer is yes. Let me try to convince you, okay? So first of all, the stupidest UV model is just where you really do have a potential phi to the n, some big phi to the n, right? And then that gives you, just talk about the abelian case, and that gives you
Yeah.
cos n5, right?
Yes.
Okay. Now, you might say, all right, now in the UV model, it's clear you have a strong coupling issue because you have a very high dimension operator. So the epsilon in front of the high dimension operator is the same epsilon in front of your IR potential, right? But you get a much smaller power of epsilon because that thing up there is, I don't know, a dimension 10 operator or something, right? And so the dependence of the strong coupling scale on epsilon, naively, you would look at the low dimension operator and say, well, it's more or less independent of epsilon because the strong coupling is coming from, you know, very high powers of phi, and then the epsilon doesn't matter anymore. But there's a mismatch. Do you see that there's a mismatch just in this very stupid simple model? There's a mismatch between a parametric mismatch between your naive estimate of the strong coupling scale from the low energy theory and the high energy theory. That should make you very, very suspicious, right? Because this is just some stupid linear signal model. So you can ask, okay, great. What's happening, you know, between these scales? Is this some kind of a CFT? And there's nothing fancy going on. What turns out is that the low energy theory also gets strong at a lower scale. If you do it carefully, if you do the unitarity business carefully, you will find that it gets strong at the same scale that this naive theory gets strong parametrically.
And do you need to use for this unitarity analysis? Do you need to use effectively n states, external states, or not?
Yeah, you have to start looking at of order n states.
Yeah. Okay.
Fair. That's totally fair because your theory does predict that.
No. Yeah, I understand. I was just trying to understand your point.
So then, since then, we've supposedly been working on a paper, and the reason I say supposedly is because Edison keeps generating ideas, and then Ricardo and I are too old to keep up with him. So we initially did this thing. So someday, I hope we'll write this paper. And there are some, you know, so except for this sort of pretty negative comment, the rest of it is all answered. Okay. But there really is a strong coupling issue here. This N really does make this low energy operator get stronger faster than you would think. Right.
Right. So now you would say that you would suspect that in the story I just told you, it's a similar situation. So
yeah,
I have
because your N is not that big, you know, but there is a parametrically for large N, there's a parametric enhancement of the strong coupling in the UV.
So what would be the scale for pi f over
I forget.
n or something?
Yeah, it's some weird power of epsilon. It's the scaling with epsilon that's weird, right? Because in the high energy theory, it's epsilon times some big phi to the n. Right? And so the strong interaction scale is a very small power of epsilon, right?
It should we go like 1 over epsilon to the
Yeah.
1 over n power?
Yeah, 1 over n minus 2 or some n minus 4 or something like that, right? And the point is that is reproduced in the low energy theory if you do it carefully. You have to look at the unitarity of many particle scattering, right?
Yes.
Oh, that'd be a problem.
Well, you have to take all of that into account. So, but the claim is that you do get, you know, these two things match. So you can understand, from that you can figure out what the result is just by doing it in the UV theory, right? I claim that a careful analysis of the IR theory, that operator would get strong at the same scale that the linear signal model operator gets strong. And if that weren't the case, then you would have all sorts of weird paradoxes about what happens in the scales in between them. You can't think of a theory that could beat. It would be some sort of interacting massless theory that doesn't exist.
Yeah, so I think I understand. If I try to, I mean, this is something I'll definitely look at. I think it's really interesting. If I try to apply this to the story, yeah, I have to reconcile it with the fact that this coefficient is so small, in a sense. So
that actually helps you. I mean, so you might be okay because
yeah, exactly.
your gamma is really small and your n is not that large. So this effect, I think, is there, but it may not be very numerically big for you. You might be fine.
No, but I understand. Okay. No, it's also interesting because definitely the story of Anson, that his paper at some level really was useful for us, even though with I mean, he's trying to do something more ambitious, if you wish, because he's really trying to get this exponential suppression of the potential that we don't.
So that doesn't work, and so then we were off to the races and trying to see what you could salvage, and there might be something you can salvage, okay, from the original idea. But yeah.
Okay, yeah. Please do write this paper.
Yeah. Edson is very patient. The problem is that both Ricardo and I are working on other papers where our contribution is actually needed. Because, you know, Edson is just on generating one idea after another, and, you know, he's just too fast for us. So we're discouraged.
In your in progress class, you have something to say? You have some preliminary examples?
Well, yeah, I can tell you what we've been thinking about, but we didn't go very far yet. So I think one thing that you can try to do if you just want to really forbid these lower dimensional operators, you could imagine that indeed there is some gauge symmetry, there is some scalar multiplet. Let me say this and then say what's the problem. Some scalar multiplet that has itself a large charge. Okay, is a large representation of this gauge group, so that, for example, the analogy with the standard model would be, instead of being able to write a Yukawa coupling with doublets to get the quark masses, you can only get a higher dimensional representation for the quark masses, and then you have to start from there. The issue is that this is not going to work. To solve the hierarchy problem, then this scalar has to be also condensate with something, and I don't know how far this really helps. So in a sense, I think I could be trading the large representation with the large representation scalar in the UV, but I'm not sure how far I'm going with this. What would be more interesting, I think, would be to write a theory where say I can write a gauge fermion theory, where I can get both spontaneous breaking the way that I want, for example, SO6 to SO5 or SU4 to SP4, say. And at the same time, I forbid really any lower dimensional operator. But I think that's harder. So sort of this I don't see how to do at the moment. Yeah, so that's what I can say. I don't know if you have ideas. I'm happy to discuss.
Other questions?
If you just try the simplest one, what end would you get?
Say it again. Sorry.
Write down some simplest model. What end could you get?
You mean by? I think I need to understand better the question. You mean by, say, choosing a certain scalar representation, or?
Yeah, your goal is to get a very large end, but I just say if you just try something very simple, what end do you get?
Yeah, no, okay. I don't think I can answer that in the sense that what I was just suggesting, in principle, I think can work, because if I choose by fiat, I choose my representation of the scalar to be large. Okay, then in principle, I'm forbidding operators below a certain dimension, but yeah, it's equivalent to saying I fix n to be 10, 20 or so by hand. So I don't think I have an answer. I don't want to. If I understand correctly the question, I cannot tell. at the moment.
Yeah, yeah, we should thank Ennio again, and people who would like to leave should leave. Thanks very much.
Thank you.
Sorry, we shouldn't have, shouldn't have made the question period so long.